The purpose of this lab was to analyze the trajectory and motion of a star orbiting a black hole of unknown mass. By analyzing the star's motion, I was able to create a code that told me the forces that were acting on the star. My code also gave me what the mass of the black hole was. We know that an object's forces, and thereby its momentum, can be broken down into parallel and perpendicular components, as stated at the bottom of this slide. Using this fact, I can reverse engineer the star's momentum in order to find the net force acting on it. Here is a deeper look at why this process works. As we know, dp dt parallel is equal to the derivative with respect to time of the magnitude of the momentum times the direction. This means that dp dt parallel only results in a change of magnitude. And we know that dp dt perpendicular is the derivative of p hat times the magnitude. And we know that that means that dp dt perpendicular will only result in a change in direction. Once we have the parallel and perpendicular components of the derivative of momentum, we can then find the net force acting on our object. Here's my glow script code for this lab. On line 11, we have the seed I used in order to get my star's trajectory. Down below that, we have some initial conditions for the lab, where I have my constant g, the star's mass, and delta t being 86,400 seconds, which is the amount of seconds in one day. And then down below that, we have my calculation loop that really gets everything and all the data we need for the lab. I start off by calculating my initial and final velocities. From there, I can find my initial and final momentums. Once I have that, I can find delta v and delta p just by subtracting the two vectors. And then with that number, I can calculate the derivative of the momentum with respect to time, which is the same thing as the net force acting on the system. From there, I can use the formulas on the previous slide to calculate the dp dt parallel, and then from that I can use a little trick to where we know dp dt is equal to the sum of the parallel and perpendicular components. Because we don't know the radius between the star and the black hole, we can rearrange the formula to get that dt perpendicular is equal to dp dt minus dp dt parallel. And with that, we know what Fnet is and the sum of its components in the parallel and perpendicular direction. Here's what my program looks like. So we know that Fnet is equal to f of g. So that means when the radius is smallest, right there, all of my forces will be the strongest, whereas when the star is the farthest away, my forces will be the smallest. Here's a graph of the net force and its components acting on the system. As you can see, when the radius is the smallest, which is the middle of the graph, the net force is the strongest. And on top of that, using this line of code, we can calculate what the mass of our black hole is. And we're going to get a range of values. However, I set this trend line right here, and I found the average value to be 1.35142 times 10 to the 34 kilograms. My answer to the what does it mean question is that they are mathematically identical, but observationally different. We can't observe forces, but we can observe momentum and then calculate those forces. For my what if question, I said that the masses must be identical to keep the trajectories of the star the same. As you can see down below, everything will cancel out, leaving the masses equal to each other.